welcome to another one of these ADD videos. Today I'm going to be discussing how to calculate the isoelectric point of an amino acid. The isoelectric point of an amino acid is the pH at which the net charge of that amino acid is 0. And this can be determined by picking pHs above and below each of the pKa's that correspond to your amino acid. I've taken this example here. This is glutamic acid. It has a side chain of a carboxylic acid here, and the pKa that is 4.3 has to do with this proton. And there's always going to be an amine group, and the pKa there is 9.7, and here we have a carboxylic acid group. Okay, so with the amine group, what happens is that either you have NH2 or NH3+, depending on the environment, and here the carboxylic acid, you have either COOH or COO-. So the way we determine that again is by picking pHs that are above and below each pKa. We start with the lowest pH of 1, is usually below everything. And then the first pKa that I have to surpass is the 2.2 of the carboxylic acid. So a pH greater than 2.2 would be 3. And when I pick that pH of 3, I make sure I don't surpass that 4.3 over here, because then I will make a mistake. So the next pH I'm going to pick has to be above 4.3, so how about 6, doesn't matter. And then I'm going to pick a pH that's above the 9.7 over here, so I'm going to go with 11. And real quick, if you remember the concept video for calculating the isoelectric point of an amino acid, if the pH of the environment is less than the pKa that you're looking at, means the environment's acidic, and an acidic environment means that it's going to donate hydrogens. So what does that mean? That means that a COO- will become a COOH with a neutral charge, and a NH2+, an NH2 will become an NH3+ with a +1 charge. Okay? So if the reverse is true, then the environment's basic, and if the environment's basic, so that's if pH is greater than pKa, and it's a basic environment, and bases accept protons or hydrogens, and we're going to have the COOHs then become charged in basic environments with a net charge of -1, and an NH3+ go to a neutral NH2. Okay? So with that in mind, we're going to plug in some numbers. So pH 1, everything's acidic, so that means all of my species will be protonated. So NH3 pluses everywhere, so that's a +1, +1, +1, right? Well, once I surpass my pKa of 9.7 here in this column, then I know I'm going to have a neutral charge, because this will go from an NH3+ to an NH2. Now, if I look at the alpha carboxylic acid, I'm going to have a acidic environment at a pH of 1, so it's going to be carboxylated and neutral. But at 3, I have now surpassed the pKa of this guy, which is what, 2.2, right? So because I've surpassed that pKa, what that means is I now have a basic environment and my hydrogen's been removed and I have a COO minus. And that's going to occur for the remainder of the pHs. Then I go on to the pKa of the R group. The R group has a pKa of 4.3, so basically it shall remain in its protonated form of neutral until I surpass 4.3, and then, oops, no, I did that backwards, didn't I? This is what happens when you make a video late at night. So, let's try that again. I'm going to be at a pH of 1, the environment's acidic, I donate a proton. Oh no, I was right. Second guess yourself when you're fatigued. So that's why you should get a good night's rest. So once I surpass that, the environment becomes basic, abstracts the proton, gives me a -1 charge. Okay. So calculating the net here is a +1. Then here I have a 0, and a -1, and a -2. If you did it correctly, you should increment by a value of 1 from each one of these steps. Okay. If you didn't, then you've done something wrong with your pH selection. So, what is important? Well, the important ones are the ones that are right here, the ones that are going from +1 to 0 and 0 to -1. Those ones are the ones that contribute to the isoelectric point calculation. So if you average the two pKs that changed from +1 to 0, so here that stayed the same, but the carboxylic, the alpha carboxylic group did change there. So one of the values in my pKa, or isoelectric point calculation, is 2.2 plus. Then I look at, where's the other change from 0 to -1 was the R group, right? So that was a 4.3 divided by 2 gives you a 3.25. And that should be the isoelectric point for glutamic acid. Alright, I hope this example video of calculating the isoelectric point of an amino acid helps. Next, we're going to do one for a small polypeptide of 3 or 4 amino acids. Thank you and have a nice day.